This is our first video of our last unit of the year. We're going to be talking about nuclear. It's a quick one. Some of it is or should be review from Earth Science. And it's kind of straightforward. Most of it, again, is in your reference table. So there's just some stuff you need to make sure you're aware of and kind of make sure that you remember. But use your reference tables. Just like organic, these last two units, it's all about being familiar or as familiar as possible. And then using your resources to help you guys, make sure you get things correct and that you understand what you're doing so you don't have to memorize as much. All right, so definitely spend most of your time prepping for the regents with other units than these last two. Plus, these are, right before it. Anyway, let's jump right in, guys. The first topic we're going to talk about is nuclei stability. So nuclei just means it's the plural form of nucleus. And that's what nuclear chemistry, guys, is dealing with, is the nucleus of atoms. So some of what we're going to talk about in this video today, as well as this unit, is review from like way back in Unit 2. Okay, so nuclear chemistry is the study of reactions that are caused by a change in the nucleus, okay, of an atom, and they become another element. All right, so we're actually going to change elements now. Okay, so we're not staying with what we originally had. Now you may be thinking, well, we've done that before. Well, we haven't changed elements. We've changed compounds, and we've broken compounds apart by changing bonds, but we have never changed elements up until this point. So this has nothing to do with electrons. It's just dealing with protons and neutrons. All right, so that's a big ticket idea right there, that it's only dealing with protons and neutrons, because that's what's in the nucleus. The electrons we don't care about. Bonding is all about the electrons. Most of what we've done throughout the year is all about those electrons, but now we're focusing on the other two subatomic particles. All right, so there's kind of two rules that govern the stability of nuclei. We've got the large atom rule and the small atom rule. The large atom rule, guys, is dealing with elements that have an atomic number greater than 83. So you're definitely going to want to have your reference tables out. So if you don't have them, pause the video, find yours, or go borrow one of mine. But that term atomic number, it's a good time for us to come back and review that. If I'm looking on my periodic table, one, you don't have to even memorize this, because your reference table on your periodic table gives this to you. There's that whole box, right, that identifies atomic mass, atomic number, electron configuration, all that stuff. Okay, so atomic number, guys, is that bold number down below. What does that atomic number mean for us? What does it tell us about the atom? And this is a review question. It tells us the number of protons. So again, just as a little review, since the regents is coming up, it's the number of protons. All right. So if we have a greater number of protons than 83, these elements are naturally radioactive. All right, they're naturally radioactive due to an unstable nucleus. Now you might be thinking, what makes them unstable? Well, we're going to jot this down over here. If something's unstable, guys, or when they become unstable, they typically have an imbalance of protons to neutrons. So their ratio of protons to neutrons is off. And what I mean by off, guys, it's not a 1-to-1 ratio or close to a 1-to-1 ratio. So those larger elements, when we get higher than 83, they have more and more protons packed into the nucleus, something we've talked about. Now you might be thinking, well, why is that such a big deal? Well, think about protons. What do we know about protons? They're positive, right? What do we know about like charges? Like charges want to repel each other. So you've got all these positive forces inside the nucleus, and then the neutrons are there to help balance that out, right? To hold the nucleus together. So once you get higher and higher up, you need more and more neutrons to hold that nucleus together, and it just becomes unstable. It doesn't stay there that long. All right, so that's the large atom rule. Greater than 83, they're naturally radioactive. They're always going to be breaking down. We'll talk more about that in the in the rest of the unit. Then we also have the small atom rule. This is dealing with elements with an atomic number less than 83. Have at least one stable isotope. A lot of them have multiple stable isotopes, but they have to have at least one. There's only one exception to that rule, and that is technetium. Okay, maybe you've looked at your reference tables in depth, like your periodic table. All right, maybe you haven't. I know it's been a while since we've dealt with the periodic table, but guys, if you take a look right now, if you look at all of them less than 83, notice their atomic masses. Okay, they have decimals. Now think about the atomic mass. What is that? That's an average. Again, good review topic here. It's an average of all the isotopes. Well, if you look anywhere on the periodic table where there's a parenthesis number, okay, that means it's radioactive. Okay, so you might even be looking through, when I look through technetium's number 43, the most stable or the most common isotope is 98, but it's still radioactive. And there's something unique about it. It's due to its number of protons. Okay, it having an odd number, specifically number 43, if you look at the other two elements around it, and this is going way deeper than we need to know. You guys just need to know that technetium's the only one that's less than 83 that's naturally kind of radioactive because it doesn't have any stable isotopes. But it goes deeper. It has to do, again, with that ratio, and because of molybdenum being next to it and ruthenium, it just doesn't work out, where if you look at their isotopes, the number of protons would have to change to help balance it out, and yada, yada, yada. It's unstable. Okay, that's the big thing you want to make sure you remember. That's the one thing that's there. So if you're looking at your periodic table and you see parentheses around a number for their atomic mass, that is a good indication that they're radioactive, okay, naturally radioactive. So a radioisotope, table N is going to help us with that. We'll talk more about that shortly. This is where it has one or more, all right, the definition of radioisotope is one or more radioactive isotopes. Of an element. What that means, guys, is they're unstable. Radioisotopes are unstable. That means they're going to be breaking down, and we'll talk about the modes of decay in our next video. So let's take a look. Within this, let's look at an example. How do we identify? One type of question you could be asked, is this a stable element or not? So nuclear symbols given to us. It should be easy for us to identify the element. Ca, right, is calcium. Its mass. Ooh, this is a good review. Now, typically, guys, where we wrote it like this, and this is how we will be writing it. Okay, for some reason these are backwards. The examples that I found, don't worry about it or stress about it. If you looked on the periodic table, you could match it up and figure that out. But we write the mass number at the top left. This is, again, a review for us, and this is the atomic number on the bottom. All right, so our mass here for this isotope is 37. Now, how we can tell if it's stable or not is we're going to go to our periodic table. If we look at calcium on the periodic table, what's its atomic mass if we were to round it to a whole number? It would be 40, okay? That would be its most stable isotope, okay? So if we're given a mass, an isotope mass, that is different from what we see on the periodic table, we can assume that that isotope is unstable. So this would be no for that stable question, because the most common one is calcium 40. All right, anything else we're going to consider to be stable. Now, again, there's more to it than what we're doing, guys. We're trying to keep it simple here, okay? So don't stress too much about it. Yes, there are exceptions to what we're talking about, but keep it simple, okay? You also have table N that can kind of help guide you. If you see it on table N, those selected radioisotopes, you know for sure that it's radioactive and it's unstable. Calcium 37 is on that list, okay? I want you guys to go through and try these next 4. Pause the video, all right? Look at your masses on your periodic table, and then try to identify if it's stable or not. So, next one, hydrogen. Its mass is 1. Is that stable? Yes, it is, because when we look at the periodic table, it's got 1.00794 for a mass, so that's essentially 1. Next one, Oxygen. Its mass in this case, this isotope is 16 from the symbol that we're given. Is that stable? Yes, it is, because oxygen's most common mass is 16. The next one is oxygen again. This mass here, though, is 14. Is that going to be stable? And the answer is no, because the most common isotope for oxygen that's stable is 16. And the last one, Neptunium. All right, its mass is 237, but notice, guys, oh, look, it's got an atomic number greater than 83, so right away you know that it's not stable. It's going to be breaking down. Okay, so a couple options as to what can happen with an unstable nucleus. Transmutation, guys, that's what's going to happen. It's the changing of a nucleus of one element into the nucleus of another by gaining or losing nucleons. Note here, always decays into a more stable element. Okay, so when something breaks down and it starts to decay, it decays into a more stable element. It's trying to be stable. Okay, it takes more energy to try to keep that unstable one together than going and breaking down into a stable one. So there's two modes of transmutation, and we're going to talk about both of them. You need to make sure you are familiar with them. And so the natural way means that it happens with unstable atoms. So this would be greater than 83. So an atomic number greater than 83. All right, those are your natural ones. So for example, if we had uranium-238, okay, now we're writing a nuclear reaction here, guys. We're going to learn how to do this in the next video when we talk about decay. But for now, we're going to figure this out. So it's going to decay into thorium-234. Okay, and this is an example of what we call alpha decay. There'll be more about this in the next video. So natural transmutation includes the following: alpha, beta, and positron emission. Okay, they're emitting those particles, and again, we'll talk about those particles in the next video. The sun is another great example of transmutation. Electron capture is another one. Okay, so throwing some terms out here, again, these are the big ones that we want to make sure and then know that, hey, the sun has got nuclear chemistry happening all the time. There's also induced or artificial transmutation, and this is where it occurs with stable atoms. All right, so we can get them to transmutate artificially, but we need some kind of high energy particles to begin the reaction and bombard the nucleus. Okay, so an example could be something like nitrogen-14. We could hit it with an alpha particle, and it would produce something like fluorine. Okay, so induced transmutation includes the following, where you can bombard, basically shoot particles at the nucleus. And then you have this thing called fusion, which is where you combine nuclei or atoms. And then you have fission, where you're splitting the nuclei. Okay? So I'm going to stop here and do a part 2 just so that this video doesn't get messed up or anything.